So this is a pretty cool example of a guessable recurrence relation. I'm not aware of any other way to solve this one except for guessing the answer and proving it with induction. And one of the reasons why some of the other methods don't work is because this is considered a nonlinear recurrence relation. So if you're used to differential equations, this would be similar to the differential equation y prime equals y squared, which is a nonlinear differential equation. So this is considered nonlinear for the same reason. You have an f of n term that's squared. So anyway, if you want to try to solve this one, you can just start doing it the same way as I've shown for the other examples. You just look at the first term. If n is equal to 0, then we have this is f0 squared. If n is equal to 1, then we have f2 is just going to be the previous term squared. So it's going to be to the 4th power. Again, we just have previous term squared, so this is just going to be f0 to the 8. And the pattern becomes pretty clear. It's just going to be f of n is just going to be f0 to the 2 to the n. And so this is the answer, and if you want to prove that this is correct, you just think of this thing as a statement. We've already proved that P1 is true because we know that f1 is equal to f0 squared. So if n is 1 here, then this is just f0 squared. So then all we have to do is suppose pk is true, and then just look at the k plus 1th term. So if we look at the k plus 1th term, this is just going to be, according to the original definition up here, this is just going to be fk squared. And we said that since we're supposing p of k is true, f of k is just equal to f0 to the 2 to the k. And so then you just have to be careful to use the exponent rules correctly here. And you'll see that this is f0 to the 2 to the k plus 1. And so this statement here, that fk plus 1 is equal to f0 to the 2 to the k plus 1, this is just pk plus 1. So pk implies pk plus 1, which means that since we also had our base case, that means that p of n is true for all n. So one interesting thing to look at in this case would be the limit. I mean, there's a lot of reasons for looking at the limit of a sequence. But if you look at the limit of this sequence, you'll notice that it's going to be, like, if you look at when this thing's going to converge or diverge, we could say that this thing is going to be, at least it's going to be bounded if f0 is less than or equal to 1 in magnitude. So this is going to be bounded if and only if magnitude of f0 is less than or equal to 1. And so the only reason I'm mentioning this is because there is like a related thing to this called Julia sets, and then there's this thing called the Mandelbrot set, which you may have heard of. And I'm not going to talk too much about them because I don't know really that much about them. But I can tell you that if we make a slight alteration to this recurrence relation, and we look at the recurrence relation fn plus 1 is equal to fn squared plus a constant, then first of all, this one can no longer be solved using guessing, and you can try that out. You'll see that the only time you can solve this is when the constant is 0. But I'm not sure if there is another way to solve these. There is a such thing as a sequence that doesn't have a way to solve it, so I'm not really too sure about that. But you can define this thing called a Julia set, or the Julia set of C is just the set of all the set of all starting points, f0, thinking of those as complex numbers, where the limit of the sequence is bounded. And so if you think about what was the Julia set of 0, this is just when C is 0, so this was just the set of all, this would just be like the set of all f0 that are less in magnitude than 1. So if you think of what this is going to be on the complex plane, this is just going to be the unit disk here. This is the real axis and the imaginary axis. So the Julia set of 0 is just a unit disk on the complex plane. But interestingly, if you look up Julia sets, like if you look it up on Wikipedia or Google Images or something, you'll see that for different values of C besides 0, they're really unpredictable, and they have like fractal-like edges and stuff. So then there's this other thing that's probably like the most popular fractal, which is called the Mandelbrot set, and that's just going to be the set of all C values, thinking of those as complex numbers, where the Julia set corresponding to it is connected. And so if you look up the Mandelbrot set, that's also pretty cool looking.